Welcome to today's lesson, Unit 4, Derivatives of Exponential and Sinusoidal Functions, Lesson 5, Derivatives of Exponential Functions. The derivative of the exponential function y is equal to b to the exponent x is simply b to the exponent x times ln of the base b. Let's take a look at example number 1 and see how we can use what we've just learned. So let's determine the derivative of each of these functions. Looking at A, we have y is equal to 2x. So using the rule that we just learned, dy by dx is simply equal to 2x ln of 2. Okay, and that's our derivative. So B, y is equal to e to the x, dy by dx is equal to e to the x ln of e. And we know that ln of e, in the last lesson, is simply equal to 1. Because ln, so e is an exponent of 1. So we're just left with the exponent, which is just 1. So it's just e to the x again, which we already know, that the function y is equal to e to the x is equal to itself. Example number 2, find the equation of the line that is tangent to the curve y is equal to 2 e to the x at x is equal to ln 3. Okay, so in example number 2, we have the function y is equal to 2 e to the x, and we're finding the equation at x is equal to ln 3. So again, we want to find y is equal to mx plus b. Okay. We want to find, excuse me, dy by dx, which is simply equal to 2 e to the x. Okay. Now subbing in for the value of x, so dy by dx evaluated for x is equal to ln 3 is equal to 2 e ln 3, okay, which is simply equal to 2 times 3, and that is just simply 6. Okay, so that is our slope, that's m. Okay, we have x, we need to find y. So y is equal to 2, and subbing in for the value of x, which is ln 3. Again, we'll have this same as the slope, which is just 6. So y is equal to 6. So we just need to find b. So 6 is equal to 6 ln 3 plus b. And remember, this 3 is inside the ln function. Okay, so we can't multiply it by 6. But I can move b. Okay, so I'm going to move this to the other side. I'm just flipping the entire equation. So b is equal to 6 minus 6 ln 3. Okay, so that's my b. And plugging into the equation of a straight line in order to get 6 minus 6 ln 3. Okay, so can I make that nicer looking? The only thing I can do here is factor out a 6. So 6 will give me x plus 1 minus ln 3. Okay, only other thing I can do is, if I really wanted to, I can actually punch that into the calculator, but that will give me decimals. So this is an exact value for ln 3. So ln 3 is an exact number, and I would probably just leave it as such. Okay, so that is the equation. Therefore, the equation is y is equal to 6 x plus 1 minus ln 3, and that is how you solve that question. So just one more reminder before we move into the next section of this lesson is that the ln e to the x is just equal to x, and e ln of x is equal to x. Okay, and the derivative of y equals to e to the x is simply just e to the x. So just something to keep in mind as we move into the next part of our lesson, in which we will start to differentiate harder functions. Let's take a look at using some of our derivatives rules in order to differentiate exponential functions. So let's look at using the product rule. Example, y is equal to x e to the x. So if we wanted to derive this function, we would simply say dy by dx, okay, it's the product rule. We have the first times the derivative of the second, which is e to the x, plus the derivative of the first, which is 1, times the second. Okay, simplifying, x e to the x plus e to the x. And the only thing I can do here is to factor e to the x out of each term, so x plus 1. So dy by dx. Okay, and that would be our solution. Up to this point, we've looked at functions of e to the x, in which x just stood alone. In this case now, in the exponent of the base e, we have another function. So instead of just x, we have 2x plus 1, which is a linear function. In this case, we will need to use the chain rule because it is a function within a function. So in those cases, the chain rule is quite useful. Okay, so y is equal to e to the 2x plus 1. Let's do it the long way first until you get used to it. So if I said that y, okay, let's first write the chain rule, dy by dx is equal to dy by du times du by dx. Okay. Okay, so y as a function of u is e to the u. So dy by du, differentiating y as a function of u, e to the u. Okay, so u, what I'm saying, is 2x plus 1. So I want to differentiate u as a function of x. Okay. In this case, it'll just be 2. So now, making my substitution back in, when I do a substitution, I need to do the chain rule. Okay, so find dy by dx. So differentiating y as a function of x, I'm going to make a substitution back in. E to the 2x plus 1 times the derivative of what's inside of what I made the substitution of u to be, okay, which is 2. So 2e to the 2x plus 1. So dy by dx. Okay, there we go. I find a lot of students have a problem with this question. So we're just going to go through how to solve this one. And you might find it already obvious how to do it, but I just do find a lot of students do make a mistake here. Okay, so let's derive this function, dy by dx. Okay, so the derivative of the first term is e to the x. Okay, so minus the derivative of the second term, which is negative e to the negative x, which is equal to e to the x plus e to the negative x. Okay, dy by dx. In this example, we're taking a look at a combination of an exponential function and a cosine function. So in this particular function, we're going to have to use the product rule. Okay, so we have an exponential function and a cosine function, a sinusoidal. So dy by dx. Okay. So what we'll do is we'll take the first, 2e to the x, the derivative of the second, so negative sine of x, plus the derivative of the first, so 2e to the x times the second. So just rewriting this, all I'm going to do now is I'm going to take this term and put it behind and just bring this forward. So 2e to the x, cosine of x, negative, so minus 2e to the x, sine of x. And I can factor out a 2e to the x from both terms, which will leave me with cosine minus sine of x. And unfortunately, I can't really reduce that any further. I don't think that there's any identities that I can use there, so I'll just leave that alone. let's go through this example. Y is equal to x squared 10x. So again, I'm going to use the product rule. Okay, in deriving this one, it's dy by dx. So the first derivative of the second, so it's 10x ln of 10, okay, plus the derivative of the first, so 2x, and the second. Okay. Simplifying. There's not much more we can simplify. Maybe we can factor. So let's factor out an x, 10x, okay? And then we're left with x ln 10 plus 2. And that is completely simplified. So let's take a look at our final example. Our final example is a little bit different. It deals with local extremas. Okay, so the local extrema of a function are the points where f of x is either a maximum or a minimum, just to recall. So in this particular example, we want to identify the local extremas of the function f of x is equal to x squared e to the x. Okay, so we have our function. So just recall that local extremas occur at critical points. Okay, so what we're actually need to find is the points where, or the values where, f prime at x is equal to 0, so our critical numbers. Okay, so first things first, we need to derive our function, and we're going to use the product rule in this case. So the first derivative of the second plus the derivative of the first and the second. Okay, so let's factor this. So we can say here we have x e to the x, and that leaves us with x plus 2. Okay. So in order for us to find this, okay, so let's just set it equal to 0. So we have our equation at least, so we can look at it. Okay, here we are. Okay, so let's find the values of x where this equation is true. We have two cases in this particular equation because we have a product. So let's take a look at each case separately. Okay, so looking at the first part of product, in fact, we actually have another part. So we actually have three cases. So let's take a look at case 1. Okay, because we have an x that multiplies to everything, if x was equal to 0, okay, the entire right side would also be 0. Okay, so x is equal to 0 is a solution, and is also a critical number. So case 2, e to the x. Okay, so with e to the x, will it ever be 0? Okay, so remember what the exponential looks like. It looks like this. So is there a case for a value of x, this is y, this is x, in which y will be equal to 0? No, so there's no solution because it's not in the domain or in the range. No solutions. No solutions. So our third case, of course, is this other bracket here. So case 3, x plus 2 is equal to 0, so x then is equal to negative 2. So our two solutions then, x is equal to 0 and negative 2. So as you recall from your previous unit, this divides our graph into 3 sections. We can go ahead and draw a table. Okay, so I've done that here for you. Okay, so these are our critical numbers. So we've got when the value of x is in between negative 2 and 0, when it's greater than 0, and when it's less than negative 2. And so we're going to test some values. So pick some easy numbers. So in this case, I'm going to pick 1 right here. Here would be negative 1 would be a good number, and then negative 3. Okay, so what we're going to do now, let's take our derivative. So I'm going to rewrite it so that we have it over here on the side. x e to the x, x plus 2. Okay, x plus 2. So if we were to plug in -3, wherever there's an x, well, e to the x will always be positive. We have a negative and a negative. So two negatives multiplied to each other will be a positive. So -1. Okay, so -1, the x is positive, and this will be a positive. So we have a negative times a positive is negative, and that's positive, so it'll be positive. Okay, so we have increasing, decreasing, and then increasing. So therefore, before we write our therefore, let's actually find the point, because it's actually asking us for the point. So let's actually find the y values that corresponds to these x values. So if we look at the original function, f at x is equal to x squared e to the x. Okay. What we can say here is then f at 0 then is just 0. So that's our 1 point, 0 and 0. So f at -2 is then -2 squared e to the -2. So it'd be 4e to the -2, which is the same thing as saying 4 over e squared. Okay, so that's our other point. So that's -2 and 4 over e to the exponent 2. Okay, so therefore, okay, since we have a -2 is a maximum and 0 is a minimum, so therefore 0, 0 is a local min, and -2, 4 over e squared is a local x. Okay, and that would be the final answer. Finally, let's check our learning, and that will conclude today. Determine the derivative dy by dx for y is equal to -e to the -4x over 4. Make your choice now. And the answer is D. Okay, and that concludes our lesson for today, and we'll see you next time.